First Spin. Welcome to First Spin, a show where I learn how to use the Parallax propeller without having any prior programming experience. And rather than do this on my own, I have enlisted the help of two experts.
Hey.
Hi, Whisker.
Hello.
Howdy.
Hi, Roy.
Hi.
How are you guys doing?
Well,
Decent.
yeah.
Tuesday. First Spin. I'm excited. We are coming up on the last couple weeks before our road trip.
It's
Yeah.
true.
It's going to be big. A big deal. And we are heading out to it's a new name. Parallax Expo at Parallax in Rockland.
Well, UPEW is actually going to be a sub-event inside of the Parallax Expo.
I guess that is true. What does UPEW stand for?
Unofficial Propeller Expo West.
Wonderful. And I believe the tickets are super cheap. So if you are in
Super
the
cheap
area,
as in free.
So if you're in the area of Rockland, California, and would like to hang out with us, please do sign up.
Roy will be there. Addie
Yes.
will be there.
Yes.
I'll be there.
Yes.
Yeah.
Joe Grant's gonna
Man.
be there.
Uh-huh.
Lots of cool
Uh-huh.
people are going to be there.
Agreed.
We're going to be hacking late into the night.
It's
well,
true.
until we get sleepy.
And we might even record some First Spin.
We're definitely bringing our production equipment with us, and we're going to try to record some episodes live at the event.
Woohoo! Maybe do
Yeah.
some interviews. That'd be fun.
Maybe have some guest people ask some questions right there.
Hey, that works.
Try to answer.
I like
so,
that.
if you guys see us there, it's going to be a black rack case and with some equipment, microphones and whatnot. Just look for, the strange people.
And maybe the puzzled look on my face.
Yeah,
Because that's generally a pretty good guarantee that that's me.
definitely come up and say hi.
Yes, please do.
Roy and I are pretty friendly. Addie will probably ask you a bunch of questions and make you record the answers.
Probably.
So,
But I'll make you look
Disclaimer.
good. Not that you don't look good already, but... All right, without much further ado, let's
Continuing where
continue
we
with
left off.
Unary Operators. I think we finished up with sign extend and post clear, post set, and all that good stuff, and we are now going on to question mark.
huh?
Question mark.
What is
Yeah.
this?
It's the random number.
Well,
Is that a
let's-
true random number?
Let's be clear. It is definitely not a random number. It is a
It's a
pseudo-random.
random
Yeah.
number.
What does that mean?
It's kind of random.
Well, pseudo is sort of,
Fake. Yeah,
pretending. That's what it means.
I see.
Yeah.
It appears random, but it's really generated by a formula.
Yeah. And the
operation.
formula in this case that's being used, I'm assuming, is a linear feedback shift register.
I don't know
Yep.
that.
It is, in fact, a LFSR, the
I
near
see.
feedback shift register.
And basically what that's doing, Addie, is it's taking the binary information in the current value
Mm-hmm.
and doing a simple little operation that feeds it back into itself.
Okay.
And then the result is the next
Iteration.
iteration. But it
But
goes
it always
through
starts the same.
it goes through every possible iteration and loops back in on itself.
Mm-hmm.
So depending where you start your number, that's your seed,
mm-hmm.
you're going to get a different pattern through.
I see. So then is there a possibility of making a truly random number in spin?
Good luck with that.
There's been discussions of it, and Chip has talked about it, and one of the ideas was using like an external piece of hardware hooked up to a pin that the external thing was sort of randomly having positive and negative, positive and zero values, and you would sample it randomly
Mm-hmm.
or sample it, and because it's changing randomly, you get random results. But even that is hard
Still.
to come up with something that is truly random.
Yeah.
I
There
see.
are some people that have done some very expensive stuff where they've been able to sample like the motion of an atom or something like that, or a molecule,
Mm-hmm.
and the random motion of that in a certain environment gives them a random number.
So
And
actually,
still,
it requires.
that's still not random. You look at a large enough set on its behavior, and it's still going to have a pattern. Getting
Oh.
true random is pretty We can't say it's impossible, but we can't do it.
I see.
Yeah.
So actually,
Right.
most microcontrollers aren't able to do true random.
Most computers, period, can't
Oh.
really
Yeah.
do useful random numbers for doing things like encryption.
Oh, I see.
Yeah, for true random. They
Okay.
do pseudo random.
Okay. So then,
Um,
what's this forward and reverse bit of?
Okay. So the propeller's random number thing, the pseudo random thing, they tap it in what they call the most significant bit and the least significant bit, which allows it to go forward and backwards through the random sequence.
Mm-hmm.
Remember how we said it
So-
was a loop?
Mm-hmm.
Right.
It's a big ring. You can move forward through the ring or backwards.
Oh.
So if you do question mark X, then you'll get a random number, right?
Mm-hmm.
If you do X question mark and X is the value that you got back from it before,
Mm-hmm.
it will walk backwards through the random numbers that you got before.
Oh.
So like you could go forward, you could get like 10 random numbers
Mm-hmm.
and then use the opposite side, the X question mark instead of question mark X, and feed it the last number you got and go backwards, and it will give you the same 10 numbers in reverse order.
Oh.
And that's mostly useful for allowing you to test algorithms by
Okay.
getting the same sequence of numbers and then testing it. But most of the time when you use this, you're just going to use it the default way with forward or backwards. Either one in
Mhm.
order is just going to give you a random number in sequence, right?
Mm-hmm.
And the way that theirs is set up is that you'll get all 4 billion different possible numbers before it repeats out of a
Okay.
32-bit value, right?
Okay. Yep.
So you can do some tricks to help you when you're getting a program up and running. You take some inputs from all over the place of things that you know are going to be all over the map,
Mm-hmm.
and use that to build the seed at which you're going to start X. Okay?
Okay.
And then that's your starting point in a 4 billion number long ring.
Mm-hmm.
So the more you can randomize where you start in the ring, the more, random it's going to be.
Right.
Okay.
So if you were to always start X at 0
Mm-hmm.
at the beginning of your program and always run it around in the same direction at the same speed, your program is going to behave exactly the same pattern every single time.
Mm-hmm.
Yeah,
Mm-hmm.
because you're going to get the exact same sequence of random numbers.
Right. Could you have like
Which is-
two circles intersect each other?
Yeah.
Mhm. There's all different kinds of complicated things you can do.
Oh.
You can like one of the common things to do is to like create a number out of the current time
Mm-hmm.
that's like, say the seconds from midnight,
Yeah.
and use that to seed the random number. And then as long as you don't start the program at the exact same second every day, then it'll be reasonably random because it'll start with a different seed each time,
Mm-hmm. Mm-hmm.
right?
Gotcha.
And
There's
like I
certain-
said before, you could, if you've got pins floating, you could just sort of pick up some inputs there. You could
Right.
take the counter, whatever it happens to be at the moment. There's all sorts
Right.
of things you could grab.
Yeah,
Oh,
to seed the number.
I see. Okay. Now, if say you want to grab a random number from the counter to use as a seed, do you do question mark?
Well, you're talking about using a not random start to, what you started X for that, and
So-
you
so
pick in
for
a
one-
random direction from X, it's always going to be one number or the other number.
Well, here I can answer her one question. You can't do question mark CNT because it's a unary operator, so it's going to try to assign the value into CNT, and CNT is read only.
Ah, I see.
So you need to use a variable that,
Okay.
or a local or global variable or a area in the DAT section or something like that
Okay.
to be the thing that you call this on, because it's going to give you the random number into the variable,
Okay. Okay.
into the slot.
All right. I probably
Okay.
need to play with it a little bit more before I know exactly what its limitations are, but
Right.
okay. And then what's that?
Decode.
Less
and
than or no?
it's a bar less than
Pipe.
vertical bar less than.
Pipe.
Pipe.
Pipe is commonly called by vertical bar pipe.
Okay, so what does it say?
So decode and encode are related.
Okay.
What decode does is, given a number from 0 to 31, it will give you the resultant value that is that bit turned on in the long. Just that bit. So if you give it 31, it will have the 31st bit, the top one, turned on, and all the rest will be 0.
How would you write that out?
So you would say, like, go to page 160 by clicking on the page 160 thing in the manual there that we're looking at. And it has an example of pin : equals pipe less than pin num. And pin num, you could put a 3 in there, and it will set bit 3 of pin on, and all the other bits will be off.
Oh.
See?
I see.
So it's allowing you to, this is really handy for doing things like setting the direction register or creating a mask for reading in and out, for reading in or setting out, because you can take this and set a certain bit on, and that's the pin that you care about, right? And all the rest are 0, and then you could, assign that to dir, and it will set that one pin to output, and the rest are inputs, right? Or you could or it with dir, and it will only change that one pin and leave the rest whatever they were. We've covered that before, but I mean, it's one handy usage is to set like a single pin on the in, out, or dir A registers.
Let me just double check here. So pipe and then a less than makes it
a decode.
So I guess I can't differentiate between the two yet because I haven't.
No, the other one is the opposite.
Okay.
Essentially.
So it does. So it turns it into a 1?
No. Well, what we have to. So the encode is going to take the value that you have, and whichever bit in there, the highest one out of 0 to 31 is on, that's what it will give you back as the number. But it'll be +1 because it has a special meaning for when none of the bits are on is 0. So if you give it a value of 0 for the encode operator, then you'll get 0 back. But if you give it any other value, then it will be whichever bit in that thing is on +1.
You notice how it says 0 to 32?
Right.
I guess I'm still confused.
So look at the example there.
Can we write?
I can try this. All right. So you've got a number from 0 to 31, which represents one of the bits in a 32-bit long, right? You do A colon equals pipe less than and the number. Say we're going for 16.
Okay.
Right? It is going to give you a long into A that has bit number 16 turned on and everything else turned off.
Okay.
Now, if you were to take that long that you got and went B colon equals greater than pipe
or
A.
Pipe. Yeah. Okay.
It's going to hand you back 17, I believe.
Right.
Pipe A, it'll give you 17.
And it's a little confusing there because they wanted to have a value for none of the bits are on equals 0.
If you were to hand encode a 0, it's going to give you 0. Because none of the bits are on, it gives you 0 back. But if you hand it one that has the 16th bit on, counting from 0, it's going to hand you a 17. Because it's counting from 1 to 32 instead of 0 to 31.
So then if there are multiple ones,
it's going to give you the highest one.
+1.
So the highest one.
So if bit 31 has a 1 in it, then
you'll
it'll
get
give you
32.
32. Now, is that like just a random number that you get, or is it? I mean,
No, it's-
not,
No,
sorry,
it's-
not random,
which-
but is it a
It's just a
number that represents, or like a binary number that represents the value 32?
Yeah, it's
Yeah,
32
just-
in binary.
All
You
right.
know,
Right.
it returns a
So
long
pin
back
num
to
will
you.
just be assigned 32, right? You'll just have 32 in there, just like as if you said colon equals 32.
She's still having a little bit of a hard time understanding that the binary number is the same as the integer decimal number that she's thinking of. And
Right.
if
Why
you want to
would
talk about it at base 10 or at, base 256 or binary, it's all the same number.
Now, what would be the point of doing that latter one, the encode?
To display which pin somebody set on,
Mm-hmm.
right? So you could read in A and then do this operator on it, and it would tell you the highest bit that was on in A. Right? When you read in A, it'll tell you which one was the highest one.
I give you a
that was turned
physical
on.
example of what Roy's saying there. You've got your 32 pins there.
Mhm.
All of them are hooked to switches, right?
Mm-hmm.
And you want to know which one, the highest one that's currently turned on.
Mm-hmm.
You could go C : equals greater than pipe in A, and that's going to hand the whole in A register through this, and this is going to spit out whichever pin is the highest up. The number of that pin, 0 through 32, none of them are on, it's going to return a 0 into it. If one or more of them are on, it's going to return the number of the pin plus 1 of the highest one.
Oh. Okay. That makes sense. I mean, I don't know when I would use it, to be honest, but okay.
Yeah, the decode one I find more useful just because it allows you to like have a constant up at the top that says I want to use pin 7, and then you can use encode to set pin bit 7 of a long to
Mhm.
on, and then or that with dir A and make that pin be an input or an
Mhm.
output, right?
Mhm.
And then you could mask that bit when you read in A by ending it with the encode, the decoded value.
You remember a couple of weeks ago when you were building up all of your counter stuff, right?
Sure.
And you had to work with a whole bunch of individual bits there that do different things.
Right.
You could use this to, build those numbers up.
I guess so. Although those
There's a
have
lot of ways
multiple,
to
those
do
have
that.
multiple ones though, in
And
'em.
that's where you get into your anding and all that sort of thing.
Which we'll be covering in the not too distant future.
Okay.
Because those are in the operators, the
Okay.
binary operators.
Okay.
Okay.
Yep. I'm pretty
good?
comfortable with that. Yeah.
Okay. So then the next one, bitwise not. This one's actually fairly easy.
No, it's not.
I think it is. So whatever
not.
your so whatever value you give it, it takes all of the bits in that value and switches them to the opposite. So all the zeros become ones and all the ones become zeros.
It's
So if,
opposite day,
so if you do like,
which is a paradox.
if
by
you
the way.
do not or exclamation point 1, then it would actually equal
-2.
Huh?
Because it takes so a 1 in binary is all zeros, and then that bottom bit is a 1.
Right. So wouldn't it turn it
And if
all
you-
into
no.
ones except for
No,
that
it
bottom
turns
bit?
it all into ones except that bottom bit, which is a 1, becomes a 0.
Right. So it wouldn't be -2, would it?
Yeah, because all ones with a 0 is equal to -2 if you translate it.
What?
Because all ones is -1.
Yeah.
So subtract
so-
1
'cause
from
one
all
byte-
ones, and it becomes -2, and -2 is represented by turning off the first bit of the long. This is starting to get into the whole binary numbers interpreted into decimal mechanism, which you're still
Wait
struggling
now.
with.
Wait. No, if you have 32 ones, except for the last one, then it equals like 2 bajillion
No,
blah
because
blah blah blah.
No, because the top bit is a 1, which means it's a negative number.
That highest bit there is a
Okay,
sign.
fine. Okay, fine. So it's a sign.
Now let me
so that
let me
represents the
let me
sign.
finish.
Uh-huh.
The highest bit there, the most significant one is a sign.
Mm-hmm.
All right,
Mm-hmm.
and it's negative
Mm-hmm.
in this case,
Mm-hmm.
and you're subtracting from 0 the rest of the bits.
So that'd be like -2 bajillion something.
Well, maybe I've got it backwards.
You've got it backwards.
Why?
You're subtracting the rest of the bits from 2 bajillion.
There you go.
2 billion.
Huh?
I said that backwards. So
Right.
what you're doing is you're taking all the bits that are left over, figuring out what number that is, and I guess it would be kind of like, because it's negative numbers, we're adding it to the most negative number that there is.
Right.
Addie's got a great look on her face right now. She's like, nuh-uh.
Well, so let's start with a simpler version of this, okay? If you have a 4-bit value
Yeah.
and it's all ones, so
Yeah.
1, 1, 1, 1,
Yeah.
and you do exclamation point in front of that,
Mm-hmm.
it'll become 4 zeros.
Okay, yeah, I understand
Right?
that.
So it's all zeros.
Yeah.
So now if you had 1, 0, 1, 0,
Yeah.
and you did the exclamation point, you would get 0, 1, 0, 1.
Yeah. I get that.
Okay.
Yeah.
So 1, 0, 1, 0 is in this case, because there would be a whole bunch of zeros after that up at the top, right?
Mm-hmm.
Then it's what, 12 or 10?
1
And then
plus
well,
4.
1, 0, 1, 0 is 10. And then 0, 1, 0, 1 is 5.
Right. Okay.
10 is A. But anyway, so you get that, but the problem is the thing that you're still not familiar with, because I don't think we've actually really ever discussed this, is that binary numbers, when you're going from decimal to binary, you get the positive way of doing it, right? You get, like, you take the 1, the first one is a 1, the
next
second
is
one is a
2,
2,
then
the
4.
next
Yeah.
one 4. That's true for negative numbers also, except that the value that the decimal number ends up being is that number subtracted from the maximum of all the bits on.
Okay, let's just do exclamation 0001. What's that gonna be? 1110, right?
Right.
Okay, so how do you get -2 from that?
Because if you had a 4-bit number, then the top sign there, the top bit would be the sign.
Okay.
And that's what I was trying to explain.
So that's fine. I'm fine with a negative number, right?
But
but then
a negative number means that all of those bits afterwards are not interpreted the exact same way as if it were a positive number.
It's not like a 1, 2, 4.
It is,
progression?
but it's that, but then you subtract that. The result of doing that, you subtract that from the maximum number of the 31 bits. It's tough to get. It's one of the I'm having a hard time figuring out a easier, better way to explain it to you. It's just, so if you took,
Well, let's do
well,
the
so
math
let's
then.
start-
Let's do the
let's
math
just-
of 1110. With 1 being a -1.
Well,
I
think of
guess.
0 as your center, and
Or-
then you've got your maximum positive number and your maximum negative number.
right.
The sign picks which one of those you're modifying with the value,
I understand
and
the
it brings
sign.
it closer to 0.
I understand positive
So-
or negative.
Well, that's you're looking at it from the way that you do base 10, and that's not how it works. So what you're doing is you've got a sign bit, and then you've got all the rest of your bits.
Yeah.
So you take all those bits and you figure out what your number is,
Yeah.
and you're subtracting that from the maximum.
Why are you
And the
subtracting that from the
sign
maximum?
picks which maximum you're working towards 0 from.
That's just the way that they do the binary decimal conversion. That's
She's
just
got a
how
new
it
face
works.
now, and I've never seen this one before. I think we're gonna break something.
It has to do with the binary twos complement math. It just works that way.
Okay, well, let's
And
solve 1110.
Stop asking so many questions.
Okay, let's just solve that. 1110. What would that equal?
well, it depends on if it's. Are we talking about as a
4-bit.
number?
4-bit number.
4-bit signed.
Right,
Yeah,
so-
yeah. 4-bit signed.
Right.
So the first
the bottom 3 bits
111, yeah.
is your number, so it'd be 011.
What do you mean 011?
Right.
The
Well,
bottom 3 bits are the
bottom 3
three
bits.
least
Oh, yes,
significant ones.
Sorry, yes. Okay,
Right, so
yes.
011.
Correct. Yes.
Right.
Yes.
So that's 6.
Okay.
But then that last bit, which is the sign, says it's a negative number.
So that's negative
But it's-
6.
No, it's not negative 6.
That's dumb. Okay.
No, it's not dumb. It's the way it works.
All right.
For this
Why
math.
is it not
'Cause-
negative? Okay.
So let's start. Let's back up.
So we're
if we
now
let
have
me
a
finish, let me
signed
finish,
6.
please. So let's start with, we have our 4-bit number. If we're counting up, when we start at 0 and we count up. When we get to 7, right?
Uh-huh.
That's 0111.
Uh-huh.
After 7, when we add 1 to it, it doesn't become 8 because it's only a 4-bit number. It wraps around and becomes negative 8.
Right? So it's negative 8.
No, but that negative 8 is 1000. And the reason is because after you have 0111, the next number in binary is 1000, which if it's unsigned, it would be an 8. But because it's signed, that top bit equals the sign.
And the number.
So it changes the meaning of all the rest of the bits. So instead of being negative 0, which doesn't make any sense, it's negative, the maximum negative number.
So it's both the sign and the number.
Well, it's the sign, and it tells you that the rest of the bits are interpreted differently when you're converting it to an integer.
What's wrong with base 10?
Because computers don't work in base 10, they work in binary.
Just make them work in base 10 and we'll be all happier.
Base
Me and Chip-
10
Me and
has
Chip have actually had a long discussion about trying to make a processor that worked in base 10.
That'd be
It
amazing.
was quite interesting. He would love to do that, but we couldn't quite come up with a good way to do it.
one of the main reasons why you don't do it is because with a transistor, it would take so many transistors to represent each place value
Mm-hmm.
that
Right.
you're losing massive amounts of silicon real estate just to do it. It would be
I
really
see.
funny to do, and people have done it with mechanical computers and analog computers. So
Right. So let's just go
So,
back to this, just
yeah.
so you can get this, because it's kind of important to understand, I think.
Uh-huh.
So you get that when you have a signed number, and in our case it's 4 bits,
Mm-hmm.
that means that it goes from negative 8 to positive 7. That's the range of that number. That's the
Okay.
maximum that 4 bits can represent when it's signed, is negative 8 to positive 7.
Okay.
But when you're counting in binary, it's just binary. It's just 1, 0, 1, and that's it, right?
Yeah.
So after you get to 7, and 7, when translated into binary, is 0, 1, 1, 1, the next binary number is 1, 0, 0, 0. And that, like I said before, and you went, well, that's dumb, but that translates to negative 8. And the reason is because the sign bit is 1, which means it's a negative number. So the rest of the bits are interpreted as how far away are we from the maximum negative number,
And the
right?
rest.
And it's 0 bit, they're all zeros. So it means that maximum negative number is 8. So 8 plus 0 is negative 8, right? Because it's the negative sign. So
From-
negative 8 plus 0 is negative 8.
Okay, so in 1110, we have the negative, And then the rest of the bits, which is 110, would equal what, 5? Is that right?
6. No, 6.
Oh, wait. 2,
110
2 and 4,
is
6. Negative 6.
And so you would say.
So then you would say.
8
so then.
plus 6 is -2.
-8 plus 6? Not plus -6.
No, plus 6. Because you already interpreted it's a negative number because we take the sign bit and say, okay, it's a negative number. So we take the other bits and we add them to the maximum negative value.
Wait, so it's a
decimal number.
Maximum negative value or maximum positive? Because I thought it was
maximum negative. So, like I said, signed numbers, the 4-bit signed number goes from maximum negative is -8 to maximum positive is +7.
Okay, so let's do. Sorry, I know we're out of time here, real quick, but let's do apostrophe or exclamation. Let's do a 3-bit number. Okay. Exclamation 001. We do this little flippy flip. It's 1 0 0. Oh, no, 110. Sorry, right?
Right. So in that case, though,
So
the range is -4 to 3.
Okay.
Because it's only 3 bits.
Right. And then
so that's -4 plus 2 is -2. Which is what 110 equals.
So then if I kept trying that, it would be the same.
Right, and so that's why when you had 1 0 0 0 0 0 1 on a 32-bit value, and you do the not, and you get all ones except the bottom one is a 0, that equals -2.
And that is a bitwise not. We'll be covering the Boolean not next week, but for this week, we are definitely out of time.
Out of time.
So thank you all for listening. You can find this show every Tuesday at firstspin.tv. We'll see you guys next week.
Bye.
Bye.
See ya.